Hello, everybody. This video is about linear functions. Linear functions are the most basic kind of function there is, and if you're not clear on what a function is, check out my video on functions. That's going to really make the whole concept rock solid for you, and then you can move into this first type of function known as a linear function, otherwise just known as a line. Lines, linear functions, and their applications are the most important concept on the SAT. So this is great for the SAT. It's great for an Algebra 1 class and any class, of course, where you've got to learn this stuff. I also do online tutoring, math, chem, physics, bio, writing, SAT, ACT, basically everything. Check out my website below and reach out if you want to talk about arranging some sessions. Okay, I hope you get something out of this video, and let's get to it. You've probably noticed that things change. Time goes by, so the time changes. The money you give to a cashier changes. Or you could change the radius of a circle. Now you may have also noticed that things change together. So for instance, if I throw a ball, as time goes by, the height of the ball will change. Or as the amount of money you give to a cashier changes, the number of candy bars she's going to give you will change. Or as the radius of a circle changes, the area of that circle also changes. Now, when things change, they also vary. And in math, something that varies is a variable. In math, we make certain things variables. For instance, all these things I've written up here can be thought of as variables in math. So time, money, the radius of a circle, and over here we have the height, the number of candy bars, and the area of the circle. Now, in another video or series of videos, I talked about functions. I suggest you check out that series before moving on to this one. It'll give you a really solid foundation in functions. Basically, a function is a rule that tells you how one variable, for instance, let's say time, connects to another another variable, height. So as time goes up by 1, what happens to height? Does height double as time goes up by 1? Or does height go down, etc., etc.? So functions relate to variables by a rule. And there are certain types of function, or we could say families of function, and they're sort of like different kinds of animals, right? Like you could say there's animals, which would be like saying there's functions, but then there's like mammals and reptiles and birds. So there's certain types of functions as well that share certain characteristics. And a linear function is the most basic type of function that we study. So this lesson is about linear functions. Now, only one of the functions I wrote here is actually linear, and that is this middle one. So the question is, why is that a linear function, but the other ones are not? So let's talk about some characteristics of linear functions. Now, as is so often the case, one of the best ways to explain something is just to give an example. So let's start off with the most basic kind of linear function, and that might be you put $5 in a piggy bank. I know you all have piggy banks. There's your piggy bank. And here you are putting $5 in there. All right, now let's make a little table that relates the amount of money you have in the piggy bank as the days go by. And we're going to do a scenario where you put $5 in the piggy bank on, we'll call it day 0. Well, let's call it day 1. Day 1, there's $5 in the bank. Now, you have a genius strategy for saving money, and that is to not put any more money in the piggy bank. So on day 2, you still have $5 in the piggy bank. On day 3, you still have $5 in the piggy bank, and I think you're getting the picture. So $5 stays in the piggy bank, okay? No matter how much time goes by. Now let's make a little graph of that. And on what we usually call the x-axis, you'll often see an x there. It really could be any letter, and we often call this the y-axis. We're going to make that the number of days. So we could also call it the d-axis, right? None of these labels matter that much. All right, so here we are going by with the days. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And on the y-axis is going to be the amount of money in the piggy bank. So we'll just call it money. And then we might choose to call that the m-axis. All right, so here's $5. Here's 10 in case you're interested. Well, as the days go by, on day 1 you've got $5. On day 2 you've got $5. On day 3 you've got $5. And you're getting the idea. So if we were to smear these together in a smear, you'd get a line. You'd get a flat line. And that is a linear function. It's the simplest kind of linear function we could come up with. So that's where we get the word linear, line. Now, something to notice here is that every time the days goes up by 1, every time we add 1 to the days, we add 0 to the amount in the piggy bank. That's what makes a function linear. And we'll see a couple examples in a minute, a couple more examples. For every set amount you go up in what we usually call the x variable, in this case we're going up by 1 each time, you go up a set amount in what we often call the y variable, in this case 0. So that has to be consistent, right? If I went up 1 here, and this went up 0, and then I went up 1 here, and this went up by 6, we don't have a linear function. This has to be consistent. Now, I talked about in my function series 3 different ways to represent a function. And here's 2 of them right here. A table of values is one way to represent a function. A graph is one way to represent a function. And an equation is a way to write a function. And an equation is the most useful because from the equation we can generate these other 2, the chart, the table of values, and the graph. So what would be the equation for this? Well, if we make the amount in our piggy bank, we call that y, and we call x the number of days, what's the relationship? What do you do to the number of days to get the amount in the piggy bank? What's the rule that makes those, that cause work with those arrows, if that makes any sense? The rule is, this is always 5, right? We don't care how many days have gone by. So look how easy this is. Y is 5, end of story. Notice x is not even showing up there. We don't care what x is. Y is 5, end of story. So if I just say y is the amount of money, I'll just go like that. Y is the amount of money is always 5. Or we could say m if we want to use m for money. M is 5. We call that a constant function. It's the absolute simplest kind of linear function. It's a flat line. Now let's look at some more interesting functions, because that's completely uninteresting. And I told you at the beginning of this video that the only linear function of the 3 I originally wrote was amount of money and candy bars you get. So you may already have some thoughts about why that's a linear function, but I'll show you that why it is in a sec. First, I want to talk about another linear function, And it's a little more interesting than the last one, don't worry. And this one is going to be, you're driving down the road at 50 miles an hour, and we're going to relate the time that goes by to the distance you travel. So time is changing, distance is changing, and they're changing together, and they're connected to each other, right? Okay, so let's try writing a table of values first. So we'll call the time going by, we'll call it t. And the distance you travel, we'll call it d. Now, if you remember in the last example, I put days in the first column, which is just like saying time, and I put money in the second column. Why didn't I do it the other way around? Well, in math and in science, you always put what we call the independent variable in the first column, which is going to end up being on that horizontal x-axis, if you remember. The independent variable is the thing that changes on its own and causes the effect on the other variable, which we call the dependent variable. So I'm saying that time, in this case, affects distance, or actually I was saying time affects the amount of money. Another way to say that is this depends on this. So time is always the independent variable when time is one of the variables, because time doesn't depend on anything. Time goes by itself. It's independent of other things. So that's why time goes in this first column, the independent variable. So remember that. Independent variable is on the horizontal axis, and it's in the first column. And if time is one of the variables, that's your independent variable, because time affects distance. Distance does not affect the time. If you drive 100 miles, time doesn't change because you did that. But when time goes by, the distance does change. Okay, so I told you that you were driving 50 miles an hour. And let's say you are leaving your house, and we're going to call that zero distance. So when you're at your house, you are 0 away from your house. And we want to know, how does your distance change with time if you're going 50 miles an hour, your distance from your house? So let's make our table of values. Time is in hours. Distance is in miles. Okay, if 0 time has gone by, you have gone 0 miles. Now, if you're driving 50 miles an hour, how far have you gone after 1 hour? You've gone 50 miles, because 50 miles an hour is 50 miles for every 1 hour. Now, after 2 hours, of course, you've gone 100 miles, because you've gone 50 more. After 3 hours, you've gone 150 miles. Is this a linear equation? Well, it sure looks like it, because, as I said before, for every set amount your one variable goes up, the other variable has to go up by a set amount. So what are those amounts? For every 1 hour that goes by on time, 50 miles goes by on distance. This time, let's try to do the equation before we do the graph. How is the distance related to the time? What are we doing to the time to get the distance? It looks like we're always multiplying by 50. That's the rule. Multiply the time by 50 and you get the distance. The way you write that as an equation is distance equals 50 times the time. And then we don't write dots anymore because We're in algebra. We just write it as 50t. That means 50 times time. There's your simple equation, simple linear equation. Now again, it's a linear equation, which means it's going to be a line. But is it going to be a flat line this time? You probably have some thoughts about that. Let's see. Horizontal axis is independent variable, first column, t. Vertical axis is dependent variable, second column, d. All right, let's mark off some hours here on the time axis. Let's mark off some distances. All right, let's graph this thing. We can think of each of entries in this table as a point. So this is the point 0, 0. That's right there. The second one is the point 150. After 1 hour, we've gone 50 miles. The next one is 100. After 2 hours, we've gone 100 miles. After 3 hours, we've gone 150 miles. Notice that your scale is allowed to be different on the two axes, right? Here, 1 is only that is that distance, but here I made 50 that distance. As long as you're consistent on each axis, it's fine to have a different length scale. And you can see that we have ourselves a line. And notice this time, I actually could plug in numbers in between my integers, 1, 2, 3. I could plug in a half an hour, right? How far have you gone in a half an hour? You've gone 25 miles. That's about right there. And in a quarter of an hour, you've gone 12.5 miles. I could put in any amount I want, and if I kept doing this forever and ever and ever, I would get all sorts of dots, and they would all smear together in a line. All right, now I'm going to make a little room here and do a little variation on this. And the variation is just going to be that instead of starting at your house, you start 100 miles away from your house. So let's look at what that would look like. And you're still going to drive 50 miles per hour away from your house. So let's make a table of values again. All right, now at time 0, remember you're 100 miles away from your house. So at time 0, your distance from your house is 100. That's different from what we had here. Here, at time 0, the distance was 0 because we started at our house. Okay, but you're still going to drive 50 miles an hour. So 1 hour later, you're 150 miles away from your house. 2 hours later, you're 200 miles from your house. And 3 hours later, you're 250 miles from your house. So once again, every time we go up by 1, 1, 1, 1, we still go up by 50 over here, 50, 50, 50. But the only difference is we now start 100 miles away. So if we graph these points, we're now going to have 0, 100. So our first point's up here. And then we have 1, 150. So that's right here. 2, 200. And 3, 250. And then if we smear it together in a line, there's our second situation. What would the equation of this second situation look like? Well, distance is still going to be 50 miles for every 1 hour that goes by, or another 50 miles. So we're still going to multiply the time by 50, but we're going to add 100 miles. Look what happens when we use that equation. Distance equals, where are we after 1 hour? Well, that just means I put in a 1 for t. Remember, that's how functions work. T is a variable. It can vary. I want t to be 1 hour. So this t is like a spot. It's like a container or a spot where I can put in any number I feel like. And I'm feeling like a 1. So after 1 hour, I have d is 50 plus 100. And we have 150. And yep, that's what we get.
after 1 hour, we have 150. So this equation here will work for the second situation. And you can visually see that the white car, let's put a white box around that equation. The white car is never going to catch up to the green car because they're both going the same speed, but the green car had a head start of 100 miles. So there is no way that the white car would ever catch up if they left at the same time. Now let's talk about some key features of all linear equations. And there's only two key features. The two most important things to remember when you're dealing with these things, both in a math class and on the SAT, is that what we call the slope and the y-intercept. So the y-intercept, y refers to this axis here. Remember, we normally call that y. It could be anything, but just when you say y-intercept, you just mean the vertical axis. So that means intercept means where it hits, where they cut through each other. So where does the white line cut through or intercept the y-axis? At 0. Where does the green line intercept or cut through the y-axis? At 100. Notice we see that number right there. So where do we see the 0 in the white line? Well, I could rewrite that as, so I'm just going to rewrite this equation now. D equals 50t plus 0. That's the same thing as this, right? Because plus 0 doesn't matter. So notice this spot, this constant number, and doesn't have a variable, so it's a constant, it's just a number. That's always the y-intercept. Now the slope, in order to talk about slope, I want to put up yet another line. And this situation is you're going 75 miles an hour, but you're still going to leave your house. So let's do a quick table of values for that. At time 0, you are 0 away from your house because I told you you started at your house. 1 hour later, you've gone 75 miles because you're going 75 miles an hour. 2 hours later, another 75, so 75 plus 75 is 150. 3 hours later, another 75, you've gone 225. Notice we fit the definition of a linear function, or the characteristic, which is this is going up by 1, this goes up by 75. Let's graph this. 0, 0, same as the white one. 175, that puts us about there. 2, 150, okay, that puts us right there. 3, 225 puts us about right there. And if we kept going, we'd get a line something like this. A little messier because I had to approximate stuff. So, of course, we noticed that this line is steeper than the others. And that probably makes sense because we're going faster. So, what is our rule now? Distance is 75 times the amount of time that goes by. Okay, so we finally have a line that's steeper, has a different number in front of the variable. Now, if, let's say you're going 75 miles per hour and you started 150 miles away, well, we can imagine that that would look like this. It would be the same steepness because you're going the same speed, but you're starting 150 miles away. So here are 4 lines. They have various y-intercepts, right? These cross at 0, this crosses at 100, this crosses at 150. And they have various what we call slopes. Slope is just steepness. And the slope is found in the number in front of the variable. So 75 is the slope of that function, 50 is the slope of that function, and 50 is also the slope of that function. Notice that any function or linear function with a slope of 50 has the same steepness. The two graphs that have a slope of 75 also have the same steepness, the pink and the purple. What is the equation of the pink line? It has the same slope of 75, so it's 75 times t, but it has a y-intercept of 150. So the general equation of a line is this: y equals mx plus b, where whatever m is the slope. Could be 75, could be 50, could be whatever. And whatever is in the position of the b is the y-intercept. That's where it crosses the y-axis. 150, 0, 100. So I'll write that in. So if a line is in this form, you can read off the slope and the y-intercept. You can tell what it's going to look like. So just give a quick example. Y equals 2x minus 5. That has a slope of 2 and a y-intercept of negative 5. So that wraps up my introduction to lines. Real quick, you should be able to identify a line, whether it's given to you in a table, as an equation, or of course on a graph. In a table, you should notice that for every set amount the x value goes up. All right, in this table it's going up by 1 each time. The y value goes up by a set amount, in this case up by 75 each time. So that is a feature, a characteristic of lines or linear equations. Then recognizing it in an equation or in formula form, you want to know that a line can be rearranged into y equals mx plus b form, where m and b are particular numbers for that particular line. So there's an example right here. Y equals 2x minus 5, d equals 50t plus 100, y equals 75t plus 150. Now, I actually want to point something out that's important, and that is that it doesn't have to be mx plus b. It could be b plus mx, right? It doesn't matter what order you add things in, so I could say y equals b plus mx. I'm just adding those in a different order. You could see lines that way. It's just typically the form, at least in the U.S., is given as mx plus b. On the SAT in particular, they do like to mix it up and make sure, keep you on your toes, that you can recognize that as a line as well. Okay, now also some equations won't look like that, exactly like mx plus b, but they can be rearranged into it, and I'm going to get into that in future videos. And then lastly, of course, lines, well, they look like lines, believe it or not, when you look at the visual representation. Stay tuned for my next video in this series on linear equations when I start going into slope, a very, very important aspect of a line, probably the most important aspect. But finally, I want to close this video by showing you why that one function I talked about at the beginning, where the number of candy bars varies with the amount of money you pay, why is that linear and not the other two equations? So let's just take a quick look at that. So if we were to compare the number of candy bars you buy and the cost of the candy bars, this would be the independent variable and this would be the dependent variable, because the cost depends on the number you buy. Let's just make this easy and say the candy bars cost $2 each. So clearly, if I buy 0 candy bars, hopefully I don't have to pay any money. If I buy 1 candy bar, I pay $2, 2 candy bars, $4, 3 candy bars, $6, and on and on. So this goes up by 1, this always goes up by 2. So it's linear. And of course that would look like, the graph of that would look like a line. It would go something like that. Now the other two examples real quick I gave were the radius of a circle changing with the area of the circle. So if I made a little table for that and I had the radius as my independent variable, I'll call that R, and my area as my dependent variable, I'll call it A. You may know, don't worry if you don't, you may know that the area of a circle is pi r squared. That's the formula. And you would find that if you started graphing things like, let's say we put in a, let's put in a 0 for radius. That would be 0 area. A 1 radius would be, I'm just going to approximate this, would be about 3. An area of 2 would be about 12. And a radius of 3 would be about 27. So in this example, notice that every time the x value, so to speak, x in this case r, goes up by 1, we're not going up by a set amount. First we go up by 3, then we suddenly go up by 9, and then we go up by whatever that is, 15, if I did that right in my head. So, not a linear equation. And if you were to graph that, plot those points, you would see it would look something like this. Well, let's do the dots. The dots would not follow a straight line. If you connected them, they would start to curve up. And then similarly for if you throw a ball in the air, I won't do the table, but I just want to contrast some nonlinear functions for you. If you throw a ball in the air from a height of 0, the ball's going to go up fast at first, but then it's going to slow down, and so that would start to look like that. So this would be the height of the ball and the time that goes by. Okay, so like I said, stick around for my next video. If it's not up yet, I'm making it. It'll be up soon. It's going to be on slope. It's going to be very helpful. Hope to see you there. I also offer online private tutoring anywhere in the world. I tutor all math up through calculus, physics, chem, bio, writing, and SAT and ACT prep. My website will be linked below, and you can see it here on the screen. Reach out. Let me know if you have any questions.